What if I tell you that we can all predict the future? Well, kind of.
The Bayesian brain hypothesis proposes that past experience builds an internal model of the external world inside our brains, and the brain constantly uses this model to explain the causes of and make predictions about our sensory input, like predicting the animal from this outline. Information processing in the brain can be separated into levels, where lower levels process sensory stimuli and higher levels deal with abstract planning or reasoning. Broadly speaking, through a process called predictive coding, higher levels send predictions about future sensory input to lower levels. Any mismatch between the prediction and the actual signal from lower levels is sent back to higher levels as a prediction error. The more prediction errors, the more the brain is surprised. Surprise is the brain's version of disorder. According to the second law of thermodynamics, nature tends towards disorder. In our bodies, increasing disorder eventually leads to disease and death. Carl Friston's free energy principle states that each organ in our body tries to minimize this disorder. So how does the brain minimize surprise or prediction error?
The first way is to predict the future better. According to the Bayesian brain hypothesis, the brain uses Bayesian inference to increase the accuracy of predictions by updating them with newly available sensory data.
The foundation of this process is Bayes' theorem, a statistical formula that considers the probability of a belief along with new evidence to yield the modified probability of that belief being true. We can break this theorem down in the context of our brain. Let's say you see a blurry thing with a bushy tail from your peripheral vision. Knowing that there's lots of squirrels where you live, the prior probability is high. The brain will expect the thing to be a squirrel. But then you notice that the tail is striped. The likelihood of it having a striped tail if it's a squirrel is low. So after taking the new evidence into account, the posterior probability decreases, meaning that the validity of your prediction that the thing is a squirrel decreases. Comparing posterior and prior probabilities gives a sense of the prediction error. The brain makes these predictions about everything around you, whether you realize it or not.
Through predictive coding, the brain not only uses its internal model to make predictions, but the internal model also learns from prediction errors, either being reinforced or changed in order to reduce future prediction errors.
The more likely the incoming sensory data is to be reliable, the higher the reliability or precision of the prediction error, and the larger influence it will have on updating the brain's internal model in a way that aligns it better with the external world.
So the second way to minimize prediction error is through active inference, or motivating certain behaviors that will increase the reliability of your sensory input. In part, the more attention you pay to a certain sensory stimulus, the higher the precision.
So in our scenario, an example of active inference would be turning your head to view the object with your central vision to get a clearer look. Now, these processes may go wrong. For instance, problems with updating these predictions can lead to false inferences, a key cause of hallucinations in diseases like schizophrenia.
Together, the Bayesian brain hypothesis and the free energy principle can model phenomena ranging from motor control to memory and emotion to neurological diseases, opening up countless opportunities for future scientific research.